Hello, everyone. Thank you for coming to this session. This session is SIG Node Intro and Deep Dive. I'm Hironori Shiina. I'm one of the Japanese contributors to SIG Node. Originally, this session was planned to be presented by 3 members of SIG Node. However, due to last-minute schedule conflicts, I'll be presenting it solo today. Still, I'm very happy to be here and share our work with all of you. Today, I have 4 main topics I'd like to cover with you. First, I'll briefly introduce what SIG Node is and what we are responsible for. Next, I'll go over some of the key updates and improvements made in recent Kubernetes releases. Then I'll highlight 2 important features that have gained a lot of attention recently, DRA and in-place pod resize. Finally, I'll wrap up by showing how you can get involved with SIG Node. So let's get started. To understand what SIG Node is, let's first take a look at the components we are responsible for. This picture has been used for introducing SIG Node. A node is drawn as a container ship. On this ship, containers represent our workloads. In short, SIG Node is responsible for everything that happens on this ship, from container launch to shutdown, and from performance to failure recovery. In addition, if there's one external component that SIG Node cannot function without, it's the API server on the top of left. So what keeps this ship afloat and moving? First, we have the kubelet, the foreman on the deck. It oversees the entire operation on the node, making sure containers are launched, monitored, restarted if needed, and eventually cleaned up. Then there's a container runtime. This is the engine room deep inside the ship. It actually powers and runs containers responding to the Kubelet commands. What about special cargo, things like ZPs or FPGAs? That's where device plugins and DRA come in. They help assign specialized hardware to the right containers. To keep our ship safe, we have a watchdog, the node problem detector. It constantly monitors for node problems and reports back to the control plane. Storage network, our containers need persistent volumes and connectivity. That's where CSI and CNI come in, handling the storage mounts and network interfaces. Each component plays a different role, but they work together like a symphony. So if we are wondering what SIG Node is really working hard on these days, it's a resource management. This is a key to efficient workloads. Now let's take a closer look at Kubelet, which is one of the core components managed by SIG Node. Some of you in the audience might be interested in contributing to the codebase. So I'll explore the Kubelet by looking at its source code structure. There are numerous subdirectories and files under Kubelet. First, I'll walk through how Kubelet manages the lifecycle of containers. This is a fundamental role of the Kubelet. First, the config package watches the Kubernetes API server. It detects when pods are added, updated, or deleted. Next, lifecycle is where Kubelet checks whether a pod can be admitted to the node. The pod package store the desired state of pods, what Kubernetes should run in. The heavy lifting happens in kube runtime and container. These are responsible for managing pods and containers by handling the runtime. They create and stop pods and manage the life cycle of containers. Kubernetes should be conscious of container types such as init containers, sidecars, regular containers, and ephemeral containers. They also handle container restarts, container restarts based on resize policy, and execute lifecycle hooks like post-start and pre-stop. So PLEG, or the pod lifecycle event generator, monitors the runtime for container state changes. If a container dies unexpectedly, Kubelet finds it out here. The status package collects the current status of pods and reports it back to the API server. Probes are implemented in the prober package. It runs liveness, readiness, and startup probes to track the health of containers. Volumes, images, and logs are also managed. In addition to managing container lifecycle, another major responsibility of Kubelet is resource management. This means making sure each pod and container gets the right share of CPU, memory, devices, and other node resources. The main entry point for resource management is the CM package, short for Container Manager. This is where Kubelet configures signals for each pod. Kubelet also manages the root signals for each QoS class, like guaranteed, burstable, and best effort. Inside the Container Manager, we have several sub-managers that handle different types of resources. The CPU manager assigns CPU to containers according to a policy. For example, it can use a static policy to dedicate cores to latency-sensitive workloads. The memory manager does something similar for memory. It can assign NUMA memory nodes to containers, helping with performance on multi-socket systems. These managers work together under the topology manager, which tries to align resource assignments, CPU, memory, devices to the same NUMA node. This improves performance for complex workloads. The device manager handles the allocation of specialized hardware devices, such as GPUs, NICs, or FPGAs. It ensures these resources are assigned to the correct containers. And as of recent releases, we also have DRA, or dynamic resource allocation. This allows devices to be allocated dynamically outside of the standard device plugin lifecycle. It's especially useful for special hardware use cases or vendor-specific behavior. Now, what happens when the node runs low on resources? That's where the eviction package comes in. It monitors node pressure and triggers eviction of pods that are consuming too much resources. So if you are interested in performance optimization, this is a great area to explore and contribute to. You can also see a much more deep dive into resource management in the past SIG Node session in London. So far, we've looked at Kubernetes core responsibilities like container lifecycle and resource management. But Kubernetes also handles many supporting tasks behind the scenes that are essential to keeping the node running smoothly. I show some of other subdirectories with short descriptions here. They manage the node and support specific features. So let's move on to the recent feature update in SIG Node. First, I'd like to introduce feature updates in 1.33, which was released this April. There were two major updates regarding pod lifecycle. The first one is in-place pod resize. This feature got promoted to beta. You can update container resources without restarting containers. I will explain the details later. The other major update is sidecar containers. This feature was graduated to ZA. Sidecar containers are also called restartable init containers. Literally, you can configure sidecar containers as init containers whose restart policy is always. A sidecar container is started before regular containers, and it is stopped after regular containers. So in this example, the sidecar container can collect all logs from the regular container throughout its lifetime. Here, I'd like to talk about updates in pod specs. Number one, user namespace is enabled by default now. By setting host users to false, a pod will run on a user namespace, where a root user in the pod is not the actual root user on the node. This feature provides security enhancement. Number two, proc mount type allows some files in the proc file systems to be exposed to a container. This feature also got beta along with the user namespace feature. Number three, the stop signal feature was added as alpha. You can customize a signal to stop a container. This feature also requires implementation in the runtime side. As far as I remember, it is already implemented in CRYO. Number 4 and 5, sweep action for pre-stop hook is an easy way to give a pod time to complete ongoing work when the pod is deleted. Now you can set 0 here if necessary for special use cases. Number 6, OCI volume mount feature is now beta. With this feature, a container can mount another container image or OCI artifact as a volume. Number 7, supplemental group policy was graduated to beta. If this policy is set to strict, groups defined in a container image are not merged when a container runs. This is a security improvement. By the way, this feature is one of the achievements of Japanese contributors. Next, these are updates in Kubelet configuration. Number 1 is image pull credential verification policy. This enforces verification of pull secrets even if the image was already pulled by another part. Number 2, tune crash loop backoff. You can reduce an initial delay and your max delay to restart a container in crash loop backoff. Number 3 is enhancement for image credentials. Enhancement for image credentials. This is led by SIGAOS. And other updates are shown here. The feature to collect the precious store information metrics from Linux kernel was implemented as alpha. There are a few enhancements in CPU policy options. They provide more precise CPU assignments. For 1.34, we are planning what feature will be enhanced. Many KEPs are being updated and reviewed now for the enhancement freeze deadline, which will come this week. So contributors are very busy now. Let's move on to the next section. I'm going to talk about two highlighted features, DRA and Impress pod resize. The first feature is DRA, or dynamic resource allocation. Honestly, I'm not so involved with this feature, but I should mention it, because DRA is one of the features in the most active development in now. The KEPs belong to SIG Node. However, this feature has been led by the device management working group that consists of various SIGs. This feature enables more flexible allocation of devices, such as GPUs, like sharing a device between containers or pods, and passing configuration parameters to devices. The core part of this feature, which is called structured parameters, is now at the beta stage. We are working to graduate it to GA in the next release. In addition, new features related to DRA have been implemented one after another. So this is a simple example of DRA usage from a sample driver. DRA was inspired by dynamic volume provisioning, so you can configure a pod in a similar way to persistent volumes. In pod specs, we define resource claims and refer to them from containers. In this case, two pods request one device respectively. The pods point one resource claim template as a resource claim. When these pods are created, two resource claims are created from the resource claim template by the controller. So different devices are allocated to the pods. These created resource claims can be seen in the container status. Let's move on to the next case. In this case, one device is shared by two containers in one pod. One resource claim template can be shared by referring to the template from two containers. Next, you can manually create a resource claim instead of a resource claim template. In this case, this resource claim can be shared among pods. These pods refer to the same resource claim by using at the bottom using resource claim name instead of resource claim template name in pod specs. You can also pass parameters to devices. This is an example of resource claim templates with configuration. In previous examples, resource claim templates are simple. They just required one single device. But this example requests two types of GPUs, sharing in time and sharing in space. You can set device-specific parameters in resource claim templates. These customized devices can be used by pods like this. Each container can specify a desired type of devices by using a request. There are more flexible uses in DRA. If you are interested, please join other sessions that focus on DRA. Then I'm trying to dive into the implementation of DRA a little. This picture shows an overview of implementation. There is a driver at the bottom of the worker node. The driver is implemented for a specific driver following the DRA framework. the driver publishes a list of allocatable resources as a resource slice object. With resource slices, the scheduler can see what resources are available and how many resources are available and where they are located. When a pod is created with a resource claim, the scheduler chooses a node for the pod by referring to resource slices. After the pod is scheduled to a worker node, Kubelet requests the driver to prepare necessary devices. Then the driver prepares devices and creates a CDI spec or container device interface spec, which is necessary for attaching devices to a container in the runtime. When the runtime creates the container, it configures the container as described in this spec for device allocation. That's the overview of the DAO implementation. If you are interested, you can try this feature with a sample driver without any specific devices. The next highlighted feature is in-place pod resize. This feature updates container resources, CPU, and memory without stopping containers. This feature was implemented in 1.27 as alpha about 2 years ago. This feature finally got a beta. If you have tried this feature at alpha, you can notice that container resources in pod status are updated much more quickly at beta. In addition, sidecar containers can be resized now. Plus, many bugs were fixed. There are still some limitations in this feature, such as decreasing memory limits. We will solve these problems in future releases. So I'd like to explain how this feature was updated from alpha. First, I'm going to show how it worked in alpha by resizing this sample pod. We can see the resource limits and requests are configured in C groups. Now we are requesting the resize by sending a patch to container resources. The progress can be observed in resize status. Proposed is set soon after the request arrives in the API server. Then Kubelet starts pod resizing. The resize status gets into in progress. If we see container C groups directory, we can observe the resize took effect soon. However, the resize status is still in progress, and container resources in the status have not been updated. After 60 to 90 seconds, the resources have been finally updated. This is how a pod is resized in alpha. Then let's resize the same pod again in 133. Now we need to specify resource sub-resource to request pod resize. Now the progress of resize is shown as a condition. The resources in the status are updated immediately, as mentioned before. This is how this feature was improved. So how can you get involved with SIG Node? There are many ways to contribute depending on your interests. First, we have something called KEP Wranglers. This is a relatively new role that started last year. KEP Wranglers help manage the process of feature development, making sure all the necessary tasks are completed by deadlines. Another area you can contribute to is the CI subgroup. This team plays a critical role in ensuring Kubernetes remains stable as a major project. They analyze failed CI tests, troubleshoot PLEG tests, This subgroup also holds weekly meetings to triage bugs and plan fixes. Of course, fixing bugs is always a valuable contribution. There are many open issues. If you are comfortable reviewing code or giving feedback on pull requests, that's also incredibly helpful. Not everyone needs to write code. Writing or improve documentation is just as important. Trying out new features and reporting your experience or any bugs you find is another great way to contribute. We also have regular SIG Node meetings where we discuss ongoing feature development and technical challenges. They held weekly, but we know that the time isn't always friendly for people in Asia. Oh, and of course, if you are ready to dive deep, you can help design or implement new feature. So that brings us to the end of the session. SIG Node is always happy to welcome new contributors. We know it's not always easy to join the meetings from Asia, but I think participation is totally welcome too. For example, I'm not able to join the meetings due to the time zone difference, but I still contribute to the community. And that's what brought me here today as a speaker. So thank you very much for joining me today. Enjoy the rest of KubeCon and Cloud NativeCon. Thank you. Do you have any questions?
Hi, thanks for the great presentation. You did a great job doing it by yourself. I had a question about where do you think the kind of future kind of hot areas for SIG Node will be? For example, ML is a very big thing, like ML devices, or what sort of things do you think will be kind of important areas that SIG Node will focus on in the future?
So can you say that again?
What areas, what features and things like that do you think that SIG Node will focus on in the future?
Future. So SIG Node is focusing on efficiency of workloads. So especially for AI workloads, we are focusing on DRA and other risk management features like pod level resources, Impress upgrade, Impress pod resize, something like that.